The Karapiro Viaduct, a critical component of the Waikato Expressway project near Cambridge, New Zealand, saw significant construction milestones in August 2014. The viaduct was part of the Cambridge section, which runs for approximately 16 kilometers. Starting south of the Tamahari interchange, the expressway extends to connect with State Highway 1 around 2.5 kilometers south of Cambridge. The overall project was undertaken to improve the safety, efficiency, and reliability of this major transport route and enhance the connection between Hamilton and Cambridge. HEB Construction, responsible for the viaduct's construction, began work on the expressway in September 2013, aiming for a completion date in late 2016. The Karapiro Viaduct itself was designed as an impressive feat of engineering. Spanning 200 meters in length and towering 40 meters above the Karapiro Gully, the viaduct required careful planning and execution due to the challenging topography and environmental considerations of the gully area. During August 2014, the construction progressed with a focus on erecting the foundational structures necessary to support the viaduct's significant weight and height. One of the primary tasks involved the installation of the viaduct's piers and supporting columns. Each of these components had to be anchored deeply into the ground to ensure stability and withstand the stresses of heavy traffic loads once operational. Due to the height and the potential seismic activity in the region, the design had to incorporate both strength and flexibility, ensuring the structure could endure dynamic forces without compromising safety. Time-lapse footage of the construction revealed the sequence of tasks involved in building such a large-scale structure. Initial groundwork saw excavation teams clearing and preparing the gully for the viaduct's supports. Next, cranes and other heavy machinery were used to move prefabricated segments into place. Each segment was carefully aligned and connected, a process that involved high-precision engineering to ensure that the final bridge would align perfectly across its 200-meter length. Environmental management also played a significant role in the viaduct's construction, as the Karapiro Gully is home to local wildlife and sensitive ecosystems. The construction team adhered to strict environmental guidelines, including erosion and sediment control to protect waterways from contamination and minimize impact on local flora and fauna. Where necessary, protective measures were implemented to safeguard native plants and reduce disruptions to the natural habitat. In addition to the Karapiro Viaduct, the wider Cambridge section of the Waikato Expressway included 3 major interchanges and 4 other bridges, each requiring substantial engineering expertise and coordination. The entire expressway project was part of a broader initiative to support regional economic growth by improving infrastructure, reducing travel times, and making the roads safer for both freight and passenger vehicles. By August 2014, the construction progress at the Karapiro Viaduct was a visual testament to the advances made since HEB construction commenced the project. While the viaduct and expressway were not yet complete, the work that had been accomplished by that point demonstrated a major engineering effort to connect communities and enhance the regional transport network. The expressway was expected to offer significant long-term benefits upon completion in late 2016, meeting the increasing transportation demands of the Waikato region. The Karapiro Viaduct, a critical component of the Waikato Expressway project near Cambridge, New Zealand, saw significant construction milestones in August 2014. The viaduct was part of the Cambridge section, which runs for approximately 16 kilometers. Starting south of the Tamahari interchange, the expressway extends to connect with State Highway 1 around 2.5 kilometers south of Cambridge. The overall project was undertaken to improve the safety, efficiency, and reliability of this major transport route and enhance the connection between Hamilton and Cambridge. HEB Construction, responsible for the viaduct's construction, began work on the expressway in September 2013, aiming for a completion date in late 2016. The Karapiro Viaduct itself was designed as an impressive feat of engineering. Spanning 200 meters in length and towering 40 meters above the Karapiro Gully, the viaduct required careful planning and execution due to the challenging topography and environmental considerations of the gully area. During August 2014, the construction progressed with a focus on erecting the foundational structures necessary to support the viaduct's significant weight and height. One of the primary tasks involved the installation of the viaduct's viaducts, piers, and supporting columns. Each of these components had to be anchored deeply into the ground to ensure stability and withstand the stresses of heavy traffic loads once operational. Due to the height and the potential seismic activity in the region, the design had to incorporate both strength and flexibility, ensuring the structure could endure dynamic forces without compromising safety. Time-lapse footage of the construction revealed the sequence of tasks involved in building such a large-scale structure. Initial groundwork saw excavation teams clearing and preparing the gully for the viaduct's supports. Next, cranes and other heavy machinery were used to move prefabricated segments into place. Each segment was carefully aligned and connected, a process that involved high-precision engineering to ensure that the final bridge would align perfectly across its 200-meter length. Environmental management also played a significant role in the viaduct's construction, as the Karapiro Gully is home to local wildlife and sensitive ecosystems. The construction team adhered to strict environmental guidelines, including erosion and sediment control to protect waterways from contamination and minimize impact on local flora and fauna. Where necessary, protective measures were implemented to safeguard native plants and reduce disruptions to the natural habitat. In addition to the Karapiro Viaduct, the wider Cambridge section of the Waikato Expressway included 3 major interchanges and 4 other bridges, each requiring substantial engineering expertise and coordination. The entire expressway project was part of a broader initiative to support regional economic growth by improving infrastructure, reducing travel times, and making the roads safer for both freight and passenger vehicles. The newly completed Shepherd Bridge in Footscray is a striking pedestrian and cycling bridge spanning the Maribyrnong River at Footscray Road. Designed to improve accessibility and safety for pedestrians and cyclists, the bridge adds a modern architectural feature to the local landscape while promoting active transport options for residents and visitors alike. The bridge installation was no small feat, requiring 3 cranes and 2 full weekends to carefully position the massive 450-ton structure into place. The construction process, though complex and labor-intensive, has been condensed into a time-lapse video that allows viewers to witness the entire operation in under 90 seconds, showcasing the precision and coordination required for such a project. With its completion, the Shepherd Bridge now provides a scenic, safe, and direct link across the river, catering to Footscray's growing cycling community and pedestrians who previously relied on shared or more congested routes. The Brunstabel Bridge, spanning the Wiesack River along the L4 Dorner Road in Austria, has served as a critical transport link since it was first built in 1939. Located at kilometer 10.58, the bridge underwent several phases of reconstruction and upgrading after sustaining significant war damage in 1945. These repairs allowed it to reopen to traffic in 1949, with further structural improvements completed in 1979 to enhance its load-bearing capacity. However, in the most recent bridge inspection, the structure was found to be in a deteriorated state that necessitated a complete replacement. The subsequent construction project aimed to create a safer, modernized bridge with minimal disruption to the ongoing traffic and increased safety features for users. The new Brunstabel Bridge project was designed to allow for uninterrupted traffic flow by building the new structure adjacent to the existing bridge. This method not only allowed for continuous traffic movement throughout construction, but also introduced significant safety enhancements. The improved ramp alignments and connection points on both sides of the bridge offered smoother transitions and better visibility, greatly enhancing the bridge's overall safety. Scheimet Consult, the engineering firm commissioned for this project, designed the new bridge as a 3-span pre-stressed concrete structure, comprising spans of 38 meters, 51 meters, and 38 meters, which together give the bridge a total length of 127 meters. The bridge's design incorporates a variable height slab beam cross-section with a height of 2 meters at the mid-span and 3.5 meters over the piers, spanning a total width of 10.5 meters. This configuration provided the needed strength and flexibility to handle both the dynamic loads from traffic and the environmental stresses posed by the river. The project was tendered by the state of Vorarlberg through an open bidding process, with the contract ultimately awarded to Wilhelm und Meer as the best-suited contractor. The construction of the bridge began in September 2013, starting with the foundational work for the two main bridge piers. These new piers were strategically positioned outside the riverbed on the steep slopes on either side of the Waisak, slightly upstream of the existing supports. To access these remote locations, a steep access road was constructed along the left bank of the river, while a secondary construction road was established on the right bank, ensuring that equipment and materials could be efficiently delivered to both sides. The foundation for each pier was anchored deep into the bedrock to avoid potential erosion from the Waisak's currents. Given the challenging terrain and the depth of the rock layer, this required the construction of foundation wells as deep as 9 meters, executed using a shotcrete method with 2 layers of steel reinforcement. In certain sections around the existing piers, shotcrete layers of up to 30 centimeters thick were added to bolster stability. The well casings were 20 centimeters thick and were constructed with meticulous reinforcement to withstand both the bridge's structural load and the natural forces exerted by the Waisak riverbed. In order to adhere to the project's ambitious timeline, construction continued through the winter months. By February 2014, the pier foundations had been completed, allowing work to begin on the bridge's superstructure. This phase involved the use of a climbing formwork system, a specialized scaffold that enables incremental elevation of the concrete form, which was ideal given the height of the bridge piers. The reinforcement cages for each pier segment were pre-assembled on the ground and lifted into position by crane, accelerating the construction rate so that each section could be completed every 2 days. On the crumbox side, a 60-meter-long and 6-meter-high retaining wall was constructed as part of the ramp alignment improvements. This phase involved excavating a portion of the hillside to create a stable embankment. To reinforce the steep slopes and prevent landslides, additional anchored walls were installed, with one 24-meter-long wall covered in limestone cladding for both structural support and aesthetic value. With the bridge deck in place, pre-stressing cables were installed and tensioned in segments. Each of the 16 cable bundles was tensioned to a force of 230 tons, creating a total elongation of up to 75 centimeters per cable bundle. This pre-stressing method not only reinforced the bridge structure, but also provided flexibility under heavy loads, extending the bridge's operational lifespan. Following the cable installation, grouting material was injected to lock the cables in place and ensure a firm bond with the surrounding concrete. As the primary structure neared completion, work on the bridge's drainage and surfacing began. In April 2015, waterproofing was applied to the bridge deck, starting with an epoxy resin primer, followed by 2 layers of plastomer bitumen, carefully bonded to prevent moisture infiltration. On top of this waterproof layer, a 14 centimeters thick bituminous track layer and a 3 centimeters thick asphalt concrete wearing course were laid to form the final driving surface. These layers were applied under stringent quality standards to ensure durability, grip, and optimal traffic safety. The Hardanger Bridge, a remarkable suspension bridge in Norway, is a monumental feat of engineering that connects the regions around the Hardanger Fjord. This ambitious project, which spans 1,380 meters, links the towns of Bu and Vallavik, overcoming geographical challenges and opening up new routes for travelers in the area. Planned to provide an alternative to the older ferry route, the Hardanger Bridge now serves as a critical infrastructure link and a testament to modern engineering and construction techniques. The bridge is the longest suspension bridge in Norway and the 10th longest globally, with a main span of 1,310 meters. The project kicked off in the winter of 2009 with initial groundwork that included blasting through mountainous terrain to construct tunnels and make way for the bridge's foundations. The Hardanger Fjord, with its dramatic and steep fjord walls, presented unique challenges that were overcome with a mix of advanced engineering solutions and careful planning. By April 2009, the tunnels that would eventually lead to the bridge had broken through near Vallavik, marking an early milestone. The summer of 2009 saw continued excavation and construction efforts, and the site of the future bridge began taking shape. Both tunnels required roundabouts that would serve as hubs for the roads leading to the bridge, a critical feature for traffic flow on both sides of the fjord. October 2009 marked another pivotal step: the pouring of concrete for the bridge pylons on the Bu side, a complex process requiring over 50 hours of continuous work to lay 900 cubic meters of concrete. Similarly, in January 2010, construction of the pylon foundation in Valavec commenced, setting the stage for the bridge's iconic towers. Using a climbing formwork system, the pylons were constructed in 4-meter increments, reaching their full height by May 2011, just in time for Norway's Constitution Day celebrations. These towering pylons, each 202.5 meters tall, form the skeletal foundation of the bridge and are visible across the fjord. In parallel with the pylon construction, the anchorage system for the suspension cables was installed. This system includes a splay chamber beneath the pylons and an anchorage chamber drilled deeper into the mountain. These features anchor the bridge's massive suspension cables securely within the mountainsides, a necessity given the fjord's high winds and seasonal storms. The saddles for the suspension cables were installed in early 2011, each weighing 23 tons and requiring precise millimeter adjustments to ensure the stability of the bridge. The bridge's cables, which form the backbone of the structure, had to be pulled back slightly to relieve stress on the pylons. Once the cables and pylons were balanced, the pylons were able to return to their original vertical positions. The installation of the bridge's massive cables began in November 2011, using a method called cable spinning. A cable spinning wheel, loaded with 4 bundles of galvanized steel wires, would traverse from VU to Valavik, adding 8 wires on each trip. The intricate process required 528 wires per strand, with each cable comprising 19 such strands. However, the winter months brought considerable difficulty. On Christmas Day 2011, the storm Dagmar struck, causing delays in cable spinning and additional technical challenges. Finally, in July 2012, after 9 months of continuous work, the cable spinning process was completed. Meanwhile, the steel components for the bridge were manufactured in Shanghai, China. These steel box girders, totaling 23 sections and weighing 7,850 tons, were then transported to Norway via the Suez Canal, a journey that took 46 days. By September 2012, the first sections arrived in Hardanger, and hoisting of these massive girders began. Each section was carefully lifted and bolted into place, gradually forming the bridge deck. The final steel section was lifted into place on November 7, 2012, completing the bridge's main span. Over the next year, finishing touches, including welding of the steel box girders, installation of guardrails, and painting, were executed to withstand the harsh Norwegian weather. Additionally, all 130 hangars, ranging from 2 to 127 meters in length, were installed. These hangars support the bridge deck and are attached to the main cables, allowing the bridge to carry vehicular traffic safely. As summer 2013 approached, the Hardanger Bridge was ready to open. A final inspection ensured every component met the strictest safety standards. The bridge officially opened to the public later that year, allowing motorists to cross the fjord without relying on a ferry. For the community and visitors, it was a momentous occasion, celebrated with a ceremony attended by local dignitaries, engineers, and workers who contributed to its construction. The Hardanger Bridge is not only an engineering marvel but also an aesthetic one, harmonizing with the natural beauty of the Hardanger Fjord. Its sleek design minimizes the visual impact on the surroundings, and the bridge deck features a pedestrian and bicycle lane, allowing people to experience the fjord up close. However, the bridge's construction raised environmental concerns, particularly regarding its impact on local ecosystems and tourism. The fjord is known for its rich biodiversity, and special measures were taken to minimize disturbances during construction. For example, construction activities that could impact water quality were carefully regulated, and efforts were made to restore natural habitats after completion. The bridge also serves as an alternative route for the E16 highway, which was frequently closed due to weather conditions. This has significantly reduced travel time and increased accessibility in the region, making the Hardanger Bridge an essential infrastructure for both locals and tourists. Following its opening, the Hardanger Bridge quickly became a significant part of Norway's infrastructure network, enhancing connectivity in the Hardanger region. The bridge has also become a popular attraction, drawing visitors from around the world to experience its stunning views and impressive scale. To maintain its integrity, routine inspections and maintenance have been scheduled, ensuring the bridge remains safe and functional for decades to come. The final construction phase was completed in 2014 with the removal of cranes and establishment of visitor facilities, including picnic areas and parking.